In part 1, I promised you that a neural network is just a stack of simple, learnable transformations trained by nudging weights to lower a loss. Nice sentence. Today we turn it into code you can actually run. Here is the thing that surprises people. The smallest working piece of a neural network, a single neuron, genuinely fits on a napkin. It takes a few numbers in, multiplies each by a weight, adds them up, and decides yes or no. And training it is a 3-line loop. So let's build one, from scratch, in a few lines of NumPy, no framework, and watch it learn to separate blue dots from white ones. Once you have seen a handful of numbers learn on your own screen, deep learning stops being mysterious for good. Let's build a neuron. The artificial neuron borrows its name, and only loosely its shape, from biology. A brain cell fires when its combined input crosses a threshold. The artificial version keeps that one idea, combines several inputs, and then decide whether to fire, and throws away everything else. This is inspiration, not a model of the brain. Don't read too much into the word neuron. Mechanically, it does 3 tiny things. It takes a vector of inputs. It computes a weighted sum, where each weight says how much that input matters, plus a bias that shifts the result. We call that sum the activation potential. P equals W dot X plus B. Then it passes that sum through an activation function to produce the output. Think of the neuron as a tiny voting machine. The weights are how much it trusts each input. The bias is its baseline lean. And the activation function is how decisively it turns the tally into a yes or a no. In NumPy, that whole thing is basically one line. The dot product of weights and inputs plus the bias through an activation. The simplest activation is the Heaviside step function. We define a function called step and give it the potential p. On the next line, p greater than 0 asks a yes or no question. NumPy returns true or false, and ace-type int converts that answer into 1 or 0. Positive means fire, 0 or negative means stay quiet. Now we define the neuron. It receives the weights W, the bias B, and the inputs X. NP dot multiplies each input by its weight and adds the products. Then plus B shifts that total, giving us the potential P. The final line sends P through step and returns class 1 or class 0. With random weights and bias, those answers are random too. And that is the whole neuron. 2 functions, 5 lines. There is no hidden cleverness inside a library. Everything this neuron does is controlled by W and B. Learning will mean finding values for those numbers that produce the right answers. Here is the whole training idea, and it is part 1's loop wearing work clothes. Show the neuron one example. Compare its guess to the correct answer. If it got it wrong, shove the weights a little in the direction that would have helped. Do that thousands of times. And the rule for the shove is beautifully simple. Let Y be the neuron's guess and T the true target. The error is just their difference, Y minus T, which for our yes or no case is always plus 1, 0, or minus 1. When the error is 0, the neuron was right, so we change nothing. Otherwise, we update the weights by subtracting the learning rate times the error times the input, and we nudge the bias the same way. The learning rate is a small number that controls how big each step is. That is the entire learning algorithm. Run that loop, and something quietly remarkable happens. The weights drift from noise into values that classify the points correctly, and they stay there. Nobody told the neuron the rule. It found it from its own errors. This tiny block is the ancestor of every training loop in modern AI. Everything else is just scale and refinement. With 2 inputs, we can actually see what the neuron is doing. Its decision depends on the sign of W0 times X0 plus W1 times X1 plus the bias. The set of points where that sum is exactly 0 is a straight line. On one side, the neuron says class 1. On the other, class 0. Training moves that line until it separates the 2 clouds of points. The weights set the line's angle. The bias slides it away from the origin. That is the whole geometry of a single neuron. It draws one straight line and picks a side. One honest note, real data is noisy, and perfect separation usually is not possible, and it is not even the goal. A neuron that draws a sensible line and gets most points right is working exactly as intended. Chasing 100% on your training points is how you memorize noise instead of learning the pattern. We will name that trap properly later in the series. Before we write this neuron in Python, let's make the equation visible. Imagine a cooling system with one input, temperature. If the day is 24 degrees, subtract a threshold of 20. The potential is 4, so the answer is yes. At 18 degrees, the potential is minus 2, so the answer is no. That subtraction is already a neuron calculation. The temperature is X. The number 1 is its weight, W, and minus 20 is the bias, B. So P equals W times X plus B. The weight controls how strongly temperature changes the score. The bias moves the point where the answer flips. When P is 0, we are exactly on the boundary. Above it, the neuron fires. Below it, it stays quiet. The symbols are not extra machinery. They are simply a shorter way to write the decision we just watched. Now add humidity. We still have the same neuron, but it receives two measurements instead of one. Temperature and humidity form an input vector x. Their two truss levels form a weight vector w. A vector is only a list of numbers kept in order. The dot product pairs the two lists, multiplies each input by its matching weight, and adds the products. Then the bias joins the total. Written out, that is W temperature times temperature plus W humidity times humidity plus B. Compressed, it is P equals W dot X plus B. With one input, the zero boundary was a point on a number line. With two inputs, it becomes a line across a plane. The weights rotate that line. The bias slides it. Now add wind as a third measurement. A third row grows inside both vectors. Another weighted term joins the sum, and the decision line lifts into a plane in 3 dimensions. More inputs do not change the rule. They only create a boundary in a space with more dimensions. A weight vector belongs to one neuron. Give the same inputs to several neurons, and each neuron has its own weight vector. Stack those vectors as rows, and you get a weight matrix, W. The individual biases become a bias vector, and the individual potentials become an output vector. So a whole layer is the same calculation written once. P equals W times X plus B, followed by an activation. Now look at a handwritten digit. A 28 by 28 image contains 784 pixels. The network does not begin by seeing a 9. It receives 784 brightness values, arranged as one input vector. The first weight matrix sends weighted combinations of those values into the first hidden layer. That layer produces a new activation vector. A second matrix transforms that vector again. The final layer produces 10 scores, one for each digit from 0 to 9. During one forward pass, bright pixels wake selected input units, weighted signals flow through both hidden layers, and the score for 9 rises highest, with 6 as a weaker alternative. A deep network looks large, but every layer repeats the same operation, and every row of every matrix is still one neuron's familiar W.X plus B. The step function is honest, but blunt. It only ever says 0 or 1, and it has a hard corner that makes it useless for the gradient-based training we will meet in Part 3. So in practice, we swap it for a smoother activation. A few are worth recognizing. The sigmoid squashes anything into a smooth S-curve between 0 and 1, which reads naturally as a probability. Tan is its cousin, between -1 and 1. The linear activation does nothing at all, returning the input unchanged, which is what you want when a neuron should predict a number instead of a class. ReLU, the rectified linear unit, passes positives straight through and clamps negatives to 0. It is cheap and it dominates modern networks. Leaky ReLU is the same but lets a small trickle through for negatives. Two things matter about the smooth ones. They are continuous, so a neuron can output a real number and do regression, not just classification. And they are differentiable almost everywhere, which is the exact property that makes backpropagation possible. Hold that thought. But note, swapping the activation does not change the neuron's limit. Its boundary is still a single straight line. Here is the classic problem that once stopped neural network research cold. It is called exclusive OR, or XOR. Two inputs, and the answer is 1 when exactly one of them is 1. Plot the 4 cases, and the two classes sit on opposite corners of a square. No straight line can separate them. Try to draw one, and you will always get a corner wrong. A single neuron can happily learn AND, OR, and NAND because each of those is separable by one line. It can never learn XOR. When Marvin Minsky and Seymour Papert pointed this out in 1969, it helped freeze funding for neural networks for years. One of the AI winters we talked about in Part 1. The fix turned out to be almost embarrassingly simple, but it took a while to become obvious, and it is where the word network finally earns its keep. The fix is to stop using one neuron and use a small team of them arranged in layers. Put 2 or 3 neurons in a first layer. Each draws its own line, carving the plane into half-planes. Then feed their outputs into a second neuron whose job is to combine those half-planes into a more complex region. Suddenly you can carve out shapes no single line could, and XOR falls immediately. This arrangement has a few names you will see everywhere. A dense network, a fully connected network, or a multi-layer perceptron. Dense because every neuron in a layer connects to every neuron in the next. The layer in the middle is called a hidden layer, and the number of layers is the network's depth. That is, the deep from Part 1. And with smooth activations, the whole 2-layer network is just a short stack of the same weighted sum then squash operation. Sigmoid of x times the first weights, then sigmoid of that times the second weights. Add more hidden layers, and it carves ever more intricate regions. That is the ladder we keep climbing, all the way to a network that reads handwritten digits. There is one honest gap in what we built today. Our from-scratch nudge rule works great for a single neuron. But once you have hidden layers, how do you know which way to nudge a weight buried in the middle when its effect on the final error passes through everything after it? Answering that is the single most important algorithm in deep learning. It is called backpropagation, and it deserves its own article. So that is exactly where we are going next. For now, just know that the gap exists and that it has a clean, surprisingly intuitive answer. So, here is everything we built. A neuron is a weighted sum of its inputs, plus a bias, passed through an activation function. Training is a loop. Guess, measure the error, and nudge the weights and bias by the error times a small learning rate. One neuron draws one straight line, which is enough for simple problems and useless for XOR. Stack neurons into layers, and the straight line limit disappears, at the cost of needing a smarter way to assign blame for errors. The short version? A neuron is activation of W.X plus B. You train it by nudging W and B in proportion to its error. And stacking neurons into layers is what lets a network learn anything interesting. In part 3, we earn the one piece we hand-waved today: gradient descent and backpropagation. What a gradient actually is, why those smooth activations matter, and how a network figures out which way to nudge every weight, even the ones deep in the middle. Bring the neuron you just built. If this helped, subscribe, and I'll see you in part 3.